Hello friends, we are back with reaction dynamics and we are almost towards the end of this rate processes. So, in our last lecture we discussed discussed how to find out the population of various states. So, we discussed infrared chemiluminescence. So, infrared chemiluminescence, and we have taken the example of gas phase reaction, that is diatomic halogen, okay, H plus Cl2 giving rise to HCl. So, it is B prime J primed plus Cl. Okay, so this guy is vibrationally and rotationally excited. Okay. So, and what is happening that this emits in the infrared region, and if we monitor this infrared emission spectra as a function of wavelength, then we should be able to find out information of this about the population of these various levels, this V prime and J prime levels. But the only problem is that we do not have any idea on on the population of ground state. What is the population pattern in the ground state, whether lowest V level is more populated or intermediate, or lowest vibration or intermediate vibrational levels. I mean, exactly, it is not possible to find out that, because everything we are getting, whatever information, it is from the excited state, vibrationally and rotationally excited state. Okay, but it's a good method, good technique in probing this population of various J and V levels. Okay, but it is, although it is selective, like for HCl or maybe for HF, you can apply this. That means your species should have capability of emitting in the optical spectroscopic region, maybe visible, maybe IR. Okay, but here we talked about this IR chemiluminescence. Next is another method is called the laser induced fluorescence. Laser induced fluorescence. Laser induced fluorescence, LIF. Okay. So, thing is that if you have a species which, when excited by specific laser frequency, then it goes to the excited state, and then from the excited state you can get fluorescence. So, this fluorescence is induced by lasers. That is why it is called the laser induced fluorescence. And the species, like that species may be your like fragments, like OH, maybe something else. It is not like like a stable chemical species that has to be there, but maybe other species of this sort may be useful, that it will give you laser induced fluorescence. Okay. So, by monitoring you know the fluorescence which we are getting, we can get lot of information on the population of various levels. Okay. So, what is the basic principle for this laser induced fluorescence? So, thing is that since we are doing excitation, laser induced means first you have to do laser excitation and followed by looking into your emission. So, VR, it is the potential energy function as a function of R. So, this is the lower potential energy surface and say this is your upper potential energy surface. Okay, I have rather potential energy diagram, not the surface, because it is a intersection, I mean a cross section of a 3-dimensional or multi-dimensional potential energy surface. So, these are the various vibrational levels, vibrational ladders. Okay. This is your excited electronic state. This is your maybe lower electronic state, that is maybe this is not the excited one, but it is the low lying maybe ground state, low lying electronic state. So, what do you do? You excite with laser and depending on the frequency of your laser, maybe it will reach over here, maybe it will reach somewhere over here also. Maybe it will originate from here, go to here, this way. So, depending on your excitation frequency, excitation energy, this gap means when this gap matches with the initial and final, then transition will take place. And if the population of this state say is more than the other one, or maybe this one is more populated, say this one is more populated compared to other, then the absorption cross section will be more, therefore correspondingly upper state population will be more. So, intensity of your emitted light will be more. Okay. So, basically we observe this means if we do this one, then do this excitation, then possibility is that maybe one or more level gets involved. So, in that case you may observe unresolved emission. Okay. So, in one case, like if you excite this way, then all possible levels are excited, but the thing is that when they will emit, okay, their emission they will emit at a particular frequency. So, from that emission frequency you will be able to get the idea of the status of the initial population. Okay. So, this is laser induced fluorescence, but the point is that maybe you can monitor the total fluorescence, like you can do another way, that is you keep your excitation beam fixed at a wavelength and you monitor the total fluorescence. Okay. That you can do. So, in that way what you do, this is your excitation beam. So, you keep on changing this excitation beam frequency, okay, and you monitor the total emitted light. So, this way also you would be able to know about the population information, and using the standard formula you should be able to gain information on what is exactly going on. I mean, what is exactly there in this I mean, with respect to the population of various levels. Okay. So, that means you excite different quantum states to an upper electronic state by varying lambda, I mean this one, and find out the, I mean, collect the total fluorescence. And this is like the absorbance spectra. Okay. But in case of absorption, it is not that sensitive, but it has this laser induced fluorescence, that is LIF, has the higher sensitivity. Okay. So, so that is in one respect it is advantageous. Okay. So, that is laser based absorption methods, and nowadays this laser based absorption methods are also developed, okay, which are also very much sensitive. Unlike simple absorbance spectroscopy, it is not that sensitive. Okay. But fluorescence, since fluorescence is a very sensitive one, depending on the fluorescence quantum yield of the substance or the quantum yield of the species that you are looking at. So, you may get huge fluorescence or you may get a little less fluorescence. So, all these are to be considered while using this LIF technique. Okay. Like, let us take one example, that is reaction of Hi with barium. Okay. So, Ba plus Hi giving rise to Bai in some at some vibrational level V prime plus H. Okay. So, here this Ba and this Hi, these are these are in the form of molecular beam. So, molecular beam. Okay. And using this LIF technique, okay, laser induced fluorescence technique, we can, since it is a very sensitive technique, we can detect these products like Bai or maybe some other. Okay. So, typical spectra that we may be getting for Bai, it is just like something like this. So, that will give you that is your lambda and this is your intensity. So, that will give you the idea of fluorescence intensity, and from that you can gain information like this one is most intense, okay, this one is lesser, and there is, you see, there is a progression, that means there is a gap, you see. So, these are typical gap corresponding to various levels. So, we can gain information of the levels present over there. Okay. Only thing is that, only requirement, what is the basic requirement, that since you are probing into this is your lower level and this is your upper level. So, this should fluoresce, I mean radiative de-excitation should take place from here to here, so that you get emission. This should be radiative. Okay. So, if there is no radiative emission, then this method will not be successful. So why do we need to need to gain information on the population of various levels. Okay, that will give you the idea of the levels. I mean the inner levels. Inner levels means electronic, associated, vibrational and rotational levels, and their population, how these levels are populated. Okay, so that will help in gaining information on the potential energy diagram for the species concerned. Okay, and that potential energy diagram is very important in determining the nature of the process. Okay, so that's why people were interested in finding out this population of various levels. Like one method I talked on this chemiluminescence, infrared chemiluminescence. Like that, this is another method which is your laser induced fluorescence method. Okay. Another important point is that many excited electronic state. Okay. So, excited electronic state may means if the species gets excited to an excited electronic level, then maybe photo dissociation result. Okay. So, when photo dissociation occurs, then suppose this is your excited level, say there is another level which is a dissociated level. Suppose you excite your sample over here, or maybe you excite over here, and then vibrational relaxation, the system gets transferred to here where there is a curved crossing. So, what happens that the system gets transferred from here to here, leading to dissociation. Like I discussed this femtochemistry, sodium iodide decomposition. Okay, there is a curved crossing. One is dissociative, another is attractive potential energy surface. So, what happens, the system gets transferred from the bound state to an unbound state, and then it dissociates. And of course, in the time scale of emission, that is the time required for the emission to occur, within the lifetime of the excited state. Okay, within the lifetime of the excited state means, suppose your excited ensemble is here. Okay, it say this is your excited state, and lifetime is basically the time required for the excited ensemble to decay to 1/8. Okay, 1/8 of its initial population. 1/8 means E is close to 1/3. It is basically 1/8 means 1/3. Okay, like log base E, that E I am talking about. So, that means the time required to go to 1/8 of its initial population, that is the time is called your lifetime. So, within the lifetime of the excited state, if this state dissociates, that is like you have like such a curved crossing, then it is a problem. You won't get any fluorescence. Okay, fluorescence quantum field is rapidly it is largely reduced. Okay, so your fluorescence will be less, therefore you may not be able to detect the fluorescence. So, these are the problems, associated problems one may encounter while doing this laser induced fluorescence. Otherwise this laser induced fluorescence is a very very sensitive technique, and of course this laser induced fluorescence, this part of the apparatus, you can attach such an arrangement with molecular beam arrangement. Okay, that where the reaction is taking place that reaction where these beams are interacting, crossing. So, there actually you shine with a laser, and of course you change the frequency, because you scan the frequency and collect the total fluorescence maybe. Okay, so you scan the frequency and collect the emission. Okay, and then record. That will give you the idea of this population. Okay, so this is one technique. Another technique could be a ionization method. Ionization methods. Okay, so resonant enhanced, resonantly enhanced, it is called the resonant enhanced multi photon ionization. Okay, it is called REMP, REMPI, REMP. Okay, excite, what you do, you excite to an upper electronic state. So, you have got your ground state. Okay, say you have your say pre-dissociation state. Pre-dissociation means before, here. Okay, your true dissociation limit may be somewhere over here and above. It is called your true dissociation limit. But before you reach true dissociation, if a curved crossing of this short is there, then maybe you get pre-dissociation. So you do not get, since the product gets dissociated, so you do not get any emission. Okay, so characteristic spectra vanishes as pre-dissociation occurs. So, say it is your pre-dissociative state. So, pre-dissociation. Okay. Okay. So, this is your ground state, this is the pre-dissociation state. So, maybe say AB, say this is AB star, and another state from pre-dissociation to another. Okay. So, it is basically 2 photons or multiple photons are required, at least 2 photons or multiple photons are required, multi-photon ionization. Okay. So, basically this one is pre-dissociative state, and if you from this pre-dissociation, if you add another photon, then you go to A, B, say plus electron. Okay. So, basically it is an ionized state. Okay. So, this is your ionization limit. So, beyond this, if you can cross, or at least if you can reach, you will get ionized products. Okay. So, in this case what you need, since you require a multi-photon ionization, a multi-photon process, then you need to have a high photon density. So, high photon density means your biphotonic process or maybe multiphotonic process will be enhanced. That is if your field strength, laser electric field is very high, then the nonlinear processes will take place, and your multi-photon absorption followed by ionization will take place. Okay. So, in this case you have to use intense laser pulse. Okay, intense laser pulse, and so you need intense laser pulse. Okay, and of course So that means this intense laser pulse will provide the photon which may be giving you to this ionized state. Maybe in some cases it may not be a single I mean this pre-dissociation step, I mean the level is such a height that maybe one photon will may not be sufficient. So you may need 2 photons over here. 2 photons are required to, I mean it is a biphotonic absorption to pre-dissociation, and when the pre-dissociation state is reached, then the because of your intense laser pulse, third photon. So this is first photon, this is your second, and this is the third photon is used to put the system to your to the ionized state. Okay. And the thing is that since ions are generated because of this ionization, because of this multiphotonic absorption process, so intense laser pulse may be third photon. Third photon will put to the ionized state. Okay. Ionized state before dissociation takes place. Okay. Before dissociation takes place. Okay. And the thing is that since ions are generated from this, you get ions. So you can detect ions, and ions are easy to detect, and it is a very efficient and sensitive technique. So ions, so easy to detect, and it's sensitive too. Okay. So this way, I mean this using resonantly enhanced multiphoton ionization, you can also find out it is a way, it is another way. Okay. And now next is quantum state populations can be measured from transition intensities. Okay. So different quantum state populations, you can find out using intensity of the transition. I mean the level which is more populated will have higher intensity of transition compared to the one which is of lower population. Okay. Another thing is velocities. I mean when you are plotting the velocity contour, then velocities can also be probed by Doppler broadening of the spectral lines, because if there is a relative motion between your detector and your ion, so the observed frequency is different compared to the actual frequency. Like when you hear the whistle of a train, okay, which is coming to you and maybe which is going away from you. Okay. Suppose that you are moving, you are riding a bicycle, and one train is coming to you in one case, and in another case say it is going away from you. So in both cases what is happening, that because of this relative motion of these two, between these two, you experience a difference, a different frequency. So that is called your Doppler shifting. So what happens that velocities can be measured by observing the Doppler broadening of the spectral lines. Okay. So maybe looking into the Doppler broadening broadening of spectral lines. We can also look into this velocities. Okay, and so these are this is another thing, and maybe like that, or maybe velocities you can find out by time of flight mass spectrometry, that is time required to fly from one say point to another. Okay, and that will depend on the mass as well. Okay, so that these are the things that one may be using. Another method is your Rydberg tagging. Rydberg tagging. Now, what is this Rydberg state? Now, Rydberg state is basically a state that is state of an atom. Okay, and these are electronically excited states. So, Rydberg state is a state of an atom which is electronically excited, okay, with energies following the Rydberg's formula. Okay, and also and they will Rydberg formula, as they converge on an ionic state with an ionization energy, means when you provide ionization energy, it will converge to an ionic state. So it's a basically, it's a highly excited state. Okay, so Rydberg state is basically very close to the ionization state, but maybe if you give the ionization energy, then it will easily converge to an ionic state. Okay, so these are very close, not much far. Okay, so this diagram is basically like you have got your ground state, okay, then pre-dissociative state, pre-dissociation stage, okay, then you have got your Rydberg state, and then is your ionization limit maybe. So this is your ionization limit. Okay. Ionization limit. Okay. So what you do? By maybe biphotonic absorption, of course with intense laser. This is your AB star, this is your AB ground state, then your AB double star, highly excited, another photon. Okay, so it is electronically excited state with energies following the Rydberg's formula, as they converge to an ionic state with an ionization energy. Okay, so they will they will be very close to ionization limit. Okay, so it's a variant of resonantly enhanced multiphoton ionization, in which the species in the species of interest is excited to a very high lying Rydberg state. Okay, so very high lying means they are very close to ionization. Okay, and it is lying very close to sufficiently close to the ionization limit. Okay, and if you under this condition, means if you do a Rydberg tagging, then if you can have a sufficiently a Rydberg state which is sufficiently close to the ionization limit, then with the help of a very little electric field. If you apply a very weak electric field, then what will happen, that this high line, this Rydberg state will lose an electron, okay, or maybe it will just simply ionize with the help of electric weak electric field. So that's why Rydberg state is a state of an state of an atom which is electronically excited state, and generally highly excited state with energies, and that is that follows the Rydberg's formula, and they converge to an ionic state. Okay, they will ultimately converge to an ionic state by supplying a little amount of ionization energy. So that's why small electric field will be sufficient. Electric field will be sufficient to do the thing. Okay, to ionize it. So it is another form of ionization method, although resonantly enhanced multiphoton ionization. So it directly transfers the pre-dissociative state to the ionization limit, but here what is done is it goes via the Rydberg state, high lying Rydberg state. Okay, so it will have a high velocity resolution. Okay, unlike your resonantly enhanced multiphoton ionization, because there is no Coulomb repulsion between the excited neutral species that is created with the help with the help of laser. Of course, in this case laser has to be focused very tightly. So laser should have tight focusing. Tight focusing means photon density is very high. Photon density is very high means your photon density high means possibility, probability of transition to a Rydberg state is more. Okay, so it is advantageous compared to REMPI, because it will have high velocity resolution, because there is no Coulomb repulsion between excited neutral species that is created in the laser pulse, laser focus. Okay, next is ion imaging. Ion imaging is another method. Okay, so this provides a direct picture of the velocity distribution. Okay, say you have got say A plus, say B2 A giving rise to AB, okay, B prime J prime plus B. Okay, so you can have a direct picture of the velocity distribution. Of the distribution, velocity distribution. So a basic diagram is, you have got a flight tube, okay, then you have got imaging detector somewhere over here, okay, and then you have got your signal over here which goes into a charge coupled device, CCD camera, CCD camera, and this is your imaging detector. this is your flight tube, okay, and you have got your ion optics. I mean, ion optics means to focus or defocus your ions, you need to have some electrical arrangement, which is called the which is called ion lens or ion something like that, ion mirror like that. So this is your ion optics, and you have your laser used to probe, okay, laser for probing, and here you send your molecular beam. This is your molecular beam. Okay. So in this case, you can have your velocity distribution pattern, because it will ions will move this way, okay, ions will move this way, it will enter and then it will move this way, it will fly, it will fly from here to here, and then you can image it. So that's a typical the typical description for schematic of an ion imaging apparatus. So ion imaging. Okay. Next is another important method which I might have already talked about in solution phase cases, which is called the pump probe technique. Okay, and this may be regarded as alternative to molecular beam approaches. Okay, and this is very useful for determining the population. So useful for determining row vibrational rotation that is row vibrational quantum, row vibrational populations. So that is the population of the this is very useful. Okay, and of course for the nascent states. So useful for determining the row vibrational population. So that means various rotational and vibrational quantum states, population of those quantum states. So to do that, pump probe technique is one of the widely used techniques. Okay, so what you do, like as an example, say you have got ozone O3. Okay, you shine with light photon. Okay, so photo dissociation leads to O plus O2. Okay, so this is your pump. Okay, and this O, nascent O, okay, in maybe in 1D state. So this this state, description, whether it is 1D or 1P or 3P, whatever. So this this term atomic terminology I have not talked about. So, you can consult any standard textbook, like a textbook on quantum chemistry by maybe Levine, maybe by Irving Walter Kimball, or maybe any standard quantum chemistry textbook where this particular thing is term symbol, that is molecular and atomic term symbols are discussed. So, actually this is beyond the scope of this current lecture. So, anyway, so this is in a 1D state. So, when this 1D, I mean O in 1D reacts with CH4, giving rise to OH, V prime J primed plus CH3. So, this is called a probe. Okay, this is called a probe. So, this basically this photon is your, I mean, H nu is your pump, and this CH4 is your probe. Okay. And then what you do, as I already told you, that laser induced fluorescence is a very sensitive technique. So, using laser induced fluorescence you can probe this OH, V prime J prime. So, then you employ this for the laser induced fluorescence methods. Okay. So, from laser induced fluorescence you can also have the information of the various V's and J states. Okay. And for this one, I mean, to probe this, to probe this OH, you have to, I mean, for this particular state you have to use another laser to probe this one. Okay. So, basically to generate the species for probing you have to use this O plus CH4 reaction to this to generate this OH. Okay. So, pulse laser of the order of, so pulsed laser may be typical ND YAG laser, which has the pulse width of the order of nanosecond, of the order of say 5 to 10 nanosecond. Okay. Is used for both pump and probe, used for both pump and probe measurements. Okay. And also in this case, to avoid collisional energy transfer in OH. So, to avoid collisional energy transfer because of if it is in under high pressure, then there will be there could be problem. So, that is why low pressure is used, low pressure and short, of course, short pump to probe pulse delay. Delay is used. That means you first excite, you first do this reaction. So, this is your pump, and then then there is CH4, so which reacts with this to produce this. The moment it is generated, you should have another pulse to probe into, because if you allow more time, there is more possibility of collision. So, more possibility of collision means collisional deactivation or maybe collisional energy transfer will lead to scrambling. So to avoid that, you should do the should have your pump probe delay less, short pump probe delay. Okay. And this is important because to know the population of these studies are important to know the population of the energetically accessible rotation vibrational levels. Okay. So that is why pump probe technique is a very significant technique. Okay. As for example, insertion reaction, initially it forms highly low vibrationally excited CH3OH, which lives for a very short time, okay, a few picosecond. Okay. So that is why that is what is required, that you should have your probe pulse, that should come, I mean that should be present over there, I mean your in the reaction mixture, I mean very close to your pump, because the problem is if you allow more time, then you are in trouble. That like here, I mean I just give an example that for certain insertion reaction, like when you get like for low vibrationally CH3OH excited, which has got lifetime, okay, of the order of picosecond, 10 to the power minus 12 second. So then it is a problem. So that means in that case, the moment your pump is there, the probe should also be present, I mean very close to that, otherwise you may miss it. Okay. So that is it is just giving you the basic idea of pump probe method in this molecular beam or maybe in gas phase reaction, pump probe technique. So what we have learned in this particular piece of lecture, that we have talked about this laser induced fluorescence, which is a very sensitive technique, okay, unlike this absorbance technique, it is a very sensitive technique. Okay. Only thing is that the upper electronic state should have fluorescence, that is the important point. Okay. So and you should get information on the population of the various V levels, vibrational levels. We have talked about this ionization methods like resonantly enhanced multi-photon ionization, REMP. So that is based on the ionization technique, because ions are easy to detect. Okay. And a slight variation of that one is REMP's slight variation is the Rydberg tagging. Rydberg tagging. So that is another a small variation of REMP that can also be used because in that case only thing is that you use multiphoton ionization, and so that you generate a highly excited atom, and with the help of a very weak electric field you ionize it. So in this case it has a good velocity resolution. Okay. Another is your technique is your ion imaging, that is also used to have a picture on the picture of your velocity distribution. Last we talked about this pump probe technique, which is an alternative to your beam measurements, molecular beam methods, okay, which is also very useful to look into the population of the various vibrational and rotational states, like rho vibrationally excited levels. So that is all for today, and we will talk, in our next lecture we will talk on this, we will come on, we will discuss this potential energy surface in the next lecture. So till then, thank you.